So now we have to come up with two functions, fn and gn, such that they satisfy these two conditions simultaneously, or say that no two such functions exist. So this problem is basically based on the definition of order notation, theta, big O, and little o of n. Is there an omega in here? Okay, there's an omega in here as well. So let's look at the first one. Is there a function fn and gn such that fn is little o of gn and fn is not equal to theta of gn? So the way I would approach this is that I usually draw figures for the order notation. That makes it easier. So what does it mean that a function fn is little o of a function gn? It means that little o means that strictly dominated by. So if I draw, if there's a graph of gn, and if it's like this, fn is probably always below it. So no matter how much you increase n, fn will never overtake gn. So that's what this graph will look like. And the second condition says that fn is not theta of gn. What does theta of gn mean? What is, yeah?
That function can be an upper and a lower bound?
Yes, excellent. So whenever I see theta, it's sort of, you can think about it as a sandwich. So whatever gn is, if I change just constant factors, it should sort of envelope or sandwich function f. So if this is f, gn should be somewhat like this. If I change constant factors, gn should serve as both as an upper bound or a lower bound. And now this says fn is not theta of gn. This is what theta of fn would look like, a function that's theta of fn. So obviously, if fn is not theta of gn, means fn is, can be little o of n. So what is a function that does both? Yes? Yeah. Yeah, easy. So if fn, this is one example, but you could come up with 1,000. So if fn is linear, and gn grows quadratically, gn will always dominate fn no matter how large n is. And you could make fn whatever you want, log n, constant. The only thing that matters is fn is strictly dominated by gn, and gn is not upper or lower bounding it by constant factors. So the second one is fn is theta of gn, and fn is little o of gn. So we just talked about the definitions. Is this possible? No. Yeah, sorry. I jumped the answer. So as that guy was going to say no. So it's not, because little o of gn means strictly dominated, so obviously gn cannot upper bound or lower bound fn. What about the third one? So the third one is fn is theta gn, and fn is not. Can you give me two functions that satisfy these two conditions simultaneously? No. Because this is the definition of theta gn, is that gn is both the upper bound or lower bound. So fn is big O of gn, and fn is omega of gn. So both of those should be true for this to hold. So obviously this is not true. Okay, perfect. And the last one, fn is omega, so we have omega now, and it's omega of gn, and fn is not order gn. What do these two together mean? What is the name for that? What is omega? Oh, little omega, perfect. So all these two together just mean that fn is little o of gn. And we came up with that in the first one. Fn could be linear, gn could be quadratic, fn could be log, gn could be n cubed, any two functions where gn strictly dominates fn. So is everyone clear the last one is just defining what little o of gn means? Little o of gn means that it's at least as Oh, wait. What? That's not right. Okay, never mind. This says that it's at least as big as Gn, and this says that it's not order Gn. So it's bigger than Gn. So no, that's not, sorry, I take that back completely. Nobody corrected me. You guys? Yeah.
Does that mean that Fn is strictly dominating Gn?
Yes. So it's opposite. So Gn is little o of Fn. Okay, good. So that was confusing. Okay, good. So this means that Fn is always at least as much as Gn. Gn could be bounding it, lower bounding it. It could be that Fn is strictly larger. But this means that Fn is not upper bounded by Gn. So this means it's not theta. It's just Fn is something sort of strictly dominating Gn. You look confused. Okay, good? All right, perfect. Any more questions? This stuff is, you just have to keep repeating the definition and draw the pictures like that, and hopefully, yes?
So what little o would be, the f of n is big O of g of n, and, no, sorry. Yeah, what would the two things be to make little o true?
Well, little o means that it's strictly, so if you want to say that Fn is little o, this is sort of little o, it looks really big. But if Fn is little o of Gn, means that Gn is order Fn, that could be true. Gn is still upper bounding Fn. What's not true is that if you said F is little o of Gn and F is theta of Gn. You see? So it could, order notation let's say that Gn is dominating, but little o means it's strictly below. So it couldn't be that theta. It's true. It could be order, Gn could be order F. Wait, Anyway, you got what to say. The more I say, the more. Yeah, okay.
We have a lower bound which is 0.
Lower bound, which is 0.
So you have an upper bound and you have a 0, and then you would have a theta 0 in the upper bound. Is that possible?
What do you mean? So it's the function is always 0.
Either it's going to be the lower bound,
Yeah.
0, so it's going to be absolute, or it has an upper bound, and something in between them. So it's either above 0, or it has an upper bound.
So you're saying, so which is Gn in that? So you're defining Fn or? Okay.
The upper bound,
Gn is some function that dominates Fn. And
the lower bound is 0.
so that's not Gn. Lower bound is some other function that's always 0, then you have Fn, and then you have Gn, something that dominates Fn.
You have a theta without having an omega.
Well, you can't, so depends on where you put the theta. If you're saying that it has to be true that Gn sort of bounds Fn on both sides. And if Gn is always 0 for any n, that means Fn can't be above it. So the 0 part is not Gn. So this picture would be that this is Fn, and somehow if I keep changing constants, Gn somehow is either here or here. So this is C1 Gn, this is C2 Gn. This 0 is some other function that's always 0. You cannot have theta. Theta would mean that I just change constant factors, and basically Fn and Gn are similar, just the same. Only difference by constant. If you have any questions, we can talk after class. But for now, I think we should move on. All right, one more. Mm-hmm. So this is a very good question. So the question, now let me repeat it. The question is that when we said Fn is little o of Gn, we said, okay, Fn can be n and Gn can be n squared. But if you just look within this chunk, 0 to 1, Fn would grow, so n squared would be smaller than n in this small region, which is why these definitions are what is called asymptotic definitions, which means that you only observe the behavior after some large n. So you cut off the initial part and you say for some there exists some large n, and if you look at all the numbers n above that chunk, this is the property that's satisfied. So for small n, there could be variations, it may not satisfy, but you have to look at what happens when n is large. When n is bigger than some capital N, think of it that way. So these definitions, what you call, is it asymptotically different? When you say, is it asymptotically different, you say, okay, forget about small values. Tell me what happens when n becomes large. Is this true or not? All right, let's move on. Okay, so today we're going to talk about data structures. So data structures are some sort of black boxes that we use when we program problems. We use some sort of data structures, and what they give us is that they sort of have some functionality, and you can use them without knowing what's inside them. So you can have some operation. A data structure can have some operations that's part of its definition, and then inside the black box is the implementation. So this is what Professor Skiena is talking about. He's saying data structures have two parts. One is the abstract operations that you can specify if you're building your own data structure, or if you're using an existing data structure, it'll come with some operations that you can, that's how you interact with the data structure. You use its operations. And the implementation is what's inside, how the data structure implements whatever functions it's implementing inside, what is the efficiency of these operations, and if you change what's inside the box, you could get some operations are faster and some are slower, and there'll be trade-offs. So right now we're intentionally talking at a very high level. So when I talk about a data structure, you should think about, okay, what are the operations of this data structure? What can I do with this data structure? Operations are sort of knobs on the data structure that you can press, and you can give in some input with each of the knob, and it will give you back some output. And implementation is what's inside, like how do I code this data structure? And when people say off the shelf, that just means, okay, exists some data structure, it's already been implemented, you just take it and you use it for whatever program you're using. So you might just take a stack or a queue or some other bigger data structure that are made up of arrays and things like that, and you just use the operations and you just use it as a black box. People always say black box, and all that means is that you just look at it from outside, you don't need to know what's inside, and you just get the operation that it says it does. So let's look at example. So you think the one kind of data structure, you can think of it as a stack, is that you have a list of items. And this is sort of a pile of items, and it gives you two operations. It says you can push a new item on it, so you have a pile, and you can add another item to it, or you can pop an item. So and pop just means take the topmost item and return it. So it gives you two things. This black box gives you two things that you can do with it. You can insert an item that it just places it on the top, and you can pop an item, it just gives you whatever is the topmost item from it. Now this seems pretty simple, like what would you even do with such a thing, but stacks are actually a small part of many other complicated data structures that you will learn about. Even algorithms will use stacks, and the way stacks work changes the way the algorithms work. And it's really important to think about is as whatever came in last is the first thing that came out. So you push something on top, and that's what came out when you popped. And we're going to talk about stacks a little bit more in a few minutes, I think later today. And the point is that you can implement this pile in different ways. So push and pop are the operations that I was talking about, and how you actually store these elements, how do you implement it inside is what we mean by implementation. So every data structure has two components. Any questions? We're going to talk in more sort of real language. We're going to take examples. So most data structures, you can sort of think about it in two ways. There are two different classes a data structure could fall in. It could be made up of contiguous elements, which is what we often refer to as an array. And contiguous is in terms of memory. So I have a pile of elements and I have to store them somewhere. One way could be that I go to my RAM, I pick a location, and I just store everything one after the other together in that location. And that's what contiguous means. And you can think of them as arrays. Hopefully we've all seen arrays before. And then the second kind of data structures that are linked, that have pointers. And linked structures, you can think, all right, let me. So suppose this is your RAM. And this is one memory location. An array would be you take all the chunks here, all the memory here, and you store it one after the other. And that's an array. And linked list would be you come up with different chunks all over the memory, and you store the location of what the next chunk is. So this is called a pointer. So you have different pieces. They could be anywhere, and the only way they're connected are through these pointers. So when you have linked list, I go here. Suppose I start from, this is the beginning of the list. I go here. My pointer tells me where to go next. It's not right after me. So I'll follow the pointer, which is just an address, as we'll talk about. A pointer is just a memory address. It says, go to this memory location. Then I read that element, and then I have another pointer that says, go to this memory location. This kind of structure is called a linked list. An array is just, you take a block of memory, and you store all your items together, and what's the good part about an array? So what's the pros of using such a data structure that sort of stores all your elements right next to each other? Yes? Yes, that's one good point. Yes, you don't need, so pointers are some additional memory that you're using. So this is whatever items you're using. Suppose these are numbers. So you're storing the numbers, and plus you're using some memory to write the address, which is the pointer. So in arrays, you don't need pointers. What else is good about arrays? Yes? Okay, awesome. It took me a while. Random access. So random access means that I could just pick an index and just go directly at an element here. In other words, arrays are indexable. So you can have a counter. Okay, you could have a counter, and you can know, like, this is the 0th position, this is the 1st position, this is the nth position. And if I tell you, give me the element at the 12th position, you can just go in directly because it's implicit. You know where it is. You know the beginning, and you add 12 to it, or 11 to it, and that's where you go, depending on what counters you're using. But if you ask me to do that in a linked list, there is no way I can just immediately go to this element. If I want to go to the 12th element, I'll go to the first one, then the second one, and the third one. I'll keep following these pointers, and that's my only way to get to the 12th elements. So I have to go from 1 to 11, and then I'll find the 12th element. Is there any, yeah? Yep. Awesome. So that's another way of saying the same thing. So when I need to access an element, it's order 1. So what's the running time here? Random access here means that I easily get to this cell. And order 1 means is what is the amount of time I need to access some element at the 12th position. Well, I didn't do anything. I had a counter. I went to the 1st position. I added some constant to it, or some counter to it, and I just went to the next cell. How much work is that? That's just order 1 work. But instead, when I said in a linked list, you have to go through from the beginning to wherever your element is. How much work is that in terms of order notation? What would searching for an element or just going to the ith position in a linked list, what is the running time of that operation? Yes? Okay, excellent. It's linear, because in the worst case, I could tell you, okay, go to the last element. And if I tell you to go to the last element and you're in a linked list, you have to go through the entire list. So you're doing order n work. And in an array, as I said, you could just go to a n, and that's where the last element is, because you can just immediately access whatever index you want in an array. Are there any cases where you would not want an array, when such a structure wouldn't be the best thing to use? What could a situation be where you wouldn't normally use an array? Yes? Okay, awesome. So when you want to insert, in a linked list, what would you do? Well, linked list, there doesn't seem to be any order to the structure. You just have these bunch of things, and you have these pointers that take you to all these things. So if I wanted to add something in my list, I would just go to the first head of the list, go to this point, and I'll just find whatever cell I can, whatever space I find, and I'll just allocate that space, and I'll add a pointer to whatever used to be the last head of the list. And this is just, I go in, I just dump whatever I wanted onto this pile. What would happen if I tried to insert in an array? And for now, let's say we're talking about a sorted array. Yes? Yes. So if your array is a fixed size, and that's all the memory you have, and I tell you, all right, insert this element at this position. Well, you have to first move everything else, because you don't have space to add another element. You might have to allocate more space, and then you have to copy everything and then insert that element in that position. What could be a way to get around this? Suppose I don't know beforehand how many elements I might have in my array. What could be a way to fix this? How much space should I use? Suppose I say we're organizing a concert. I don't know how many people could come. So should I just allocate? I need to store the list of the names. So I need the database of all the names. Should I just start with an array that's really huge, like 1 billion names or something, and then say, okay, I'm sure I'm not going to run out? Is that a good way, or what's wrong with that? I'll just pick a really large number, and I'll set my array to that size. What's the problem with that? Yes?
You're potentially wasting a lot of memory?
Yes, I'm wasting a lot of memory. Thank you. I'm wasting a ton of memory. So what is another way? Suppose I don't want to waste a lot of memory. How should I, and I can't anticipate how many people are going to show up. How else could I use an array and get around this? Yes? Okay, perfect. So he said dynamic arrays. So now my array is somehow dynamic in a way that every time I want to insert something, it'll always let me. It'll do something, it'll sort of grow in size, and it'll always have room for any element. So we're going to learn about how to actually implement such a dynamic array, because it seems really wasteful if my array, every few sort of inserts, is just sort of, you have to allocate new space, you have to copy everything. That sounds really inefficient. But if you were using a linked list, you'd just throw this name in. But as we talked about, you couldn't really search for this name fast enough. So one important thing to remember is that not either of them are not inherently good or bad. You have to look at your use case. What kind of operations are you going to be doing more? And then choose which of these suits your needs for that. So if you really want to search, you better use an array. But if you're just going to insert and delete things and you're never going to look for anything, you should probably use a linked list. So the key point here is that no matter what sort of structure you come across, there'll be some trade-offs in the operations you have to do. And then you have to decide what is the most important operation to you and maybe optimize based on that. So let's look at what we already talked about, like what do we get out of an array? So an array is a structure which is a fixed size. So you start with some chunk and you place it in memory, and it's all contiguous. And the good time is that we already talked about you get constant time access, which is what we were talking about, order 1 random access. You just go to the index and you get whatever you want at that location. And as someone else pointed out, that you don't need to waste space storing pointers. So you're just storing the things you want to store. You're just storing elements. And because there are no pointers, arrays are actually really easy to work with. So if you've ever programmed something, if you have a choice, arrays, they're much more flexible. You don't have to do pointer manipulation. Anybody who's implemented that knows it's not fun. So they're easy to work with. And then the third point is actually comes up a lot more when you're implementing things in the real world. So what I mean by that is that arrays actually give you what we call is cache efficiency. So oftentimes when you study algorithms in more depth, you not only want to optimize operation count, you also want to optimize what we call as reads and writes from disks. So your data is stored somewhere else, and you're reading it into your cache. So it's really wasteful if you're just reading one thing at a time. You might as well, if you're reading something, if you're putting in the effort of traveling to another place, which is your disk, and bringing things back, it takes a lot of cost to do that. So in that trip, you might as well bring the next 50 things with you, because you have space and you don't want to make that trip again. So think of your data being on some drive, or your memory being sort of external, and what your cache is, that's sort of internal. So arrays, because they're contiguous, you can bring all that all at once. So that's good, because all the elements are right next to each other. If you're going to pick one, you might as well bring all of them. And then next time when you have to do an operation on any of those elements, they're in your cache. So you don't have to make that trip again. So this is one of the more sort of practical advantages of an array. It doesn't change the order notation or the running time that you would see in an order notation. But this is actually a real-time benefit that you get when you're using an array. And as someone mentioned, what happens when we are inserting into arrays and we run out of space? We have to make sure that we can handle that situation. And an array that can handle inserts even when it's full, it sort of grows in size or shrinks in size if you're doing too many deletes. That kind of array is called the dynamic array. So what we want out of this array is you start up with some small space that you allocated. It could be even 1. Start off with an array of size 1. And now I'm just inserting and deleting and maybe searching in this array. And no matter how much I insert or delete, that changes the size. My array should be able to incorporate that. And the way dynamic array works is that you insert things, and the array, when it gets full, it doubles in size. You keep inserting things, it gets full, it doubles in size, and so on. And it's exactly what you think it would do. It would just, I'll start with an array of size 1. Suppose I insert an element 2. I insert another element. Oops, I don't have space. What does the second array mean? I have to allocate another array in memory with size 2. I'll have to copy this 2 and copy whatever this next number is, insert whatever this next number is here. Then I insert another number. Okay, I don't have space. So I go in, I allocate an array of size 4. I not only have to insert the next number, I have to copy over the previous things and then insert whatever the next number is. Now I get another insert. I have space, that's good, so I insert it here. Now I insert another number, I run out of space again, and I double. So this time, what's the size of my array? It's like 16. I won't even draw. So I started with an array of size 1, I doubled, and then doubled, and then doubled. Seems like we're wasting a lot of time allocating space and copying things over. Every time my array gets full, I have to double in size, copy everything, and then keep doing this over and over. How many times would I have to double this? Suppose I have n elements, and I want to insert all of them. How many times will my array double in size? How many times will I have to go through this process. Yes? Yes, what is the base? Okay, awesome. So why will we double? Why will we double log base 2 of n, and then we'll have enough space to store n things? Does everybody understand how this math works? So here I have size 2 to the order of 1. This is 2 to the 2, 2 to the 3. No. All right, I missed an 8. Should be 8 here. 2 to the 3, 2 to the 4. And each time my array is of size 2 to the I, if I am at the ith step. So what should I be so that I have n space? I have n slots. Well, that's, and you take log on both sides, so you get, wait, what am I doing? Yep, thank you. You guys will notice this. Every time you teach a lecture and go up to the board and there are like 100 people facing you, your IQ just drops. It's true. It's like, try teaching a class like at some point, and you just go up to the board, and just by being in this proximity, you just can't think. So I'm glad you guys are helping me out. So this is how we get log n, log base 2 of n. This is how many times I need to double if eventually I'm going to have n things in my array. So do you think that this is wasteful? So let me tell you, we want to calculate what is the amount of work I'm doing if I insert n things. What is the total amount of work do you think I'm doing when I keep doubling and keep copying? Now we know we do log base 2 of n doubling. So give me an upper bound, a big O, of how much work do you think will definitely, I'm never doing more than that. So give me a big O of some running time that you think is the work required after I've done n inserts into this array. So we're trying to analyze any upper bound. It could be a bad upper bound, but any upper bound, yes. N squared, that's an upper bound. Well, you're inserting everything once. How many things are you inserting? N. At every step, how much work you're doing. Well, you're not doing more than linear work, because that's how many elements you have. Even if you doubled every single time, that would be n squared work. So this is definitely doing something better than that. I'm not doubling every other time. I'm doubling only when my array gets full. And yeah, initially it looks like it doubles every time, but let's look at some step which is where you have an array of, say, size 2 to the 5. And I double this, I get an array of size 2 to the 6. What are these numbers, by the way? What is 2 to the 5? 32? All right, thank you. What is 2 to the 6? 64. So when I go from 32 to 64, you can see I can do 32 inserts before I actually need to double. So it's definitely better than n squared, because n squared means that every step I am doing n amount of work, so I'm doubling every step, so I get n squared. Yes? N log n, that's absolutely true. We definitely don't do worse than n log n. And what would be how would you analyze that?
Because the way I see it, when you insert an element, you have to go through the array list.
Mm-hmm.
Always okay. Maybe log n.
It's always another tip for algorithms. Always say like log n or n log n. Like every time you need to give any running time, just throw it in a log n or an n log n. Oftentimes it's the right answer, trust me. They always want you to say n log n or log n, depending on the situation. So we already analyzed that the number of times we double is at most log n. How much work are we doing? Yes?
So for every time you double, you're doing at least n plus 1 copies? Or n
Well,
plus 1 insertion?
well, am I doing it every time, though? The last step, I'm copying n things, but
Every time you double,
yeah.
you do an extra n plus 1 steps.
Do I? N is big. Say n is 2 to the 50. Look at the first few steps. How many things am I copying? I'm copying 2, then I'm copying 4. So yeah, in the worst case of my last step, I'm copying n things. So I'm doing n work. So let's look at the other direction. So I have this entire thing of the array doubling. I start with 1, and then 2, and then suppose this is n. What is the step before this? I have n over 2. What about these last half, the later half of the array? How many times have they been copied? How many times have they been moved from one space to the other? So they've been inserted all right. How many times they've actually been copied? Once, right? They've only been copied when, oh, sorry, they have not been copied 0. They've been copied 0 number of times. They've been touched once when they were inserted. So these elements actually never go through a copy. How many times these n over 4 to n over 3, this n over 4 and n over 2, how many times do these elements go through a copy? Once, right, when you bring them here. So clearly, we don't do n work at every step. So n log n was a right upper bound because, well, you almost, this is, how long is this? This is log n, right? We talked about there can only be these many doubling operations. So this is log n, and at any time, you at most do n work. Think, how many copies could you possibly do at any of this step? Well, you can't do more than n. So one way to give a rough upper bound is say, all right, I have, this is the height of this, how many times am I doing this? It's log n. And at any step, the worst I could do would be I would copy n things. So I get an upper bound of order n log n. Is there a better analysis? Are we doing order n copy at every step? No. As we just realized that some elements don't get copied at all. Some elements get copied only once. Some element, if we keep sort of going back, think of it as a reverse thing. Some elements only get copied twice. So there has to be a way to analyze this sort of special behavior, and it should give us a better running time because we're overestimating a lot in n log n. Do people see why there's, we can smell that it's probably better than n log n, but we're definitely sure that n log n is an upper bound. You can never do more than n log n work. All right, so this is an analysis, and it's, it seems a little complicated, but we'll go over it slowly. And what we're going to get in the end, and the moral should be that even though it seems like we're doing a lot of work, it turns out the number at the end would be really small. It says that we're only doing 2n work. If we had a regular array, how much work would we do if we insert n things? Well, we touched n things, and we had sort of order 1 operation if I had an n space to start with. So each time I insert an element, I'm just putting it in the slot, so I'm doing constant work, and I'm inserting n things, so I'm only doing n work if I had a regular array which had been allocated n slots. How much work am I doing if I'm doing this doubling business? Well, it turns out I'm not doing more than twice n. So I'm only doing twice the amount of work I would do in a regular n size array. And this is what is sort of surprising about this. It seems like we're wasting a lot of time, but when you actually analyze it, it turns out to be a lot better. You can improve the analysis that you're coming up with. So this expression, what does this mean? We're going to go over this slowly. We were doing it right here. So n over 2 things only get copied once. No, actually, they never get copied once. But you do insert them, so that's one amount of work. So n things, how much work, n over 2, the last n over 2 things, how much work do? You do 1 unit of work. So let's start summing this up. So n over 2 things, I'm just touching them once. That's how much work I'm doing for this part. Then, how much is this? This is n over 4. We decided that we're only copying it once, and they were inserted once, so I'm only doing 2 units per element. Once they were inserted and once they were copied. How many of them they are? They are n over 4. Let's keep doing these. These are n over 8. They were copied how many times? They're copied. Wait, is he counting inserts or not? All right, so here if I is 1, we get n over 2 and we get 1. All right, we did that. Then we get n over 4, and then I is 2. Then I is 3, you get n2. Okay, we're doing it right. So this, when you have n 8th element, you do work on them thrice, they get copied twice, and then they get inserted once. And then this is sort of a pattern. And all that summation does is it writes it in notation. So this is I, and this is n2 to the I, because that's the size of the array when you're going back from 1 to log n. So why is this log? Because that's how long this is. That's how many times you're doubling. Why is this expression the way it is? Well, you look at it from top down. Yes, top down or bottom up, depending on where the top or bottom is. But anyway, so this, just keep thinking about the same thing. These n over 2 things you only touched them once because they never got copied. These n over 4 things, you copied them once and you inserted them once, so you only did 2 units of work on it. And then look at these n over 8 things. Well, you copied them twice, you inserted it once, so that's 3. And each size grows as 2 to the I. So it shrinks, or in some ways here it shrinks as a as a power of 2. I feel like this is getting complicated, but if you write this out, you write out what I is, and you write it as a sum. Yes? Doubling takes order n work. Yeah. Well, we're trying to argue that it does better than that. It only takes order n work in the last step, right? When you had n over 2 things, you got full, and you came up with the big array of size n, and you copied those n over 2 things. You did one for each of those n over 2 things. You copied them. And then after that, you inserted n over 2 things. So yes, overall, if you analyze the total of that, you did order n work at the last step. So there's a lot of different ways you can analyze an algorithm. And we're trying to look at every element, and we're looking at how many times was that element copied, or at every element, how much work was performed on that element. And how many elements they're n. So we're just going to say there are n things. Each of them, we did x amount of work. So overall, we did n times x work. And that's one way to analyze an algorithm. And they could be, so you could come up to me and have another argument that say you did order n work because the last step was sort of the biggest step of your process. And if you do the summation, that last step dominates. And it's an absolutely fine argument. So when you sort of want to squint away a little bit and just want to get a sense and not do the math, you can think of it this way. At the last step, you did n amount of work because you copied n over 2 things and then you inserted the rest. So whatever, as a whole, if you look at that, that's n amount of work. And everything else is sort of dominated by this. So everything else becomes lower order terms when you do the summation, which is why you end up getting twice n when you actually do the math. So one way, very hand-wavy way to argue this is that, well, my last step was my most expensive step. I did order n work in the last step, or I did n work in the last step. Everything else was dominated by that. So if I sum up all of the work I did, it will never be bigger than this because that's the most expensive step. And that's another way of arguing that you get some order and amount of work. Here, he actually wants to find out what the order is, and turns out the constant is just 2. And it's not important to know how the series converges. So if you look at the summation, you can take n out, and then it just becomes a series. And you're doing the summation, I through log n, you have I over 2 to the I. And turns out this series actually is at most 2. I don't know how actually that works. But we do know what is this part. If I remove the I in the numerator, what is the sum of that series? If I only had sum I 1 through log n, 1 over 2 to the I, what would that series be? What would a sum be that is half plus 1/4 plus 1/8 plus 1/16? Yes. Yes, exactly. That'd be 1. And that's sort of something we learn, how that series converges to 1. And turns out if you have this factor I on top, it actually is at most 2. And one way to at least believe it and not prove it is that I grows sort of very slowly. So basically 1 over 2 to the I grows really fast. So 1 over 2 to the I is really small. So even if you multiply I to it and add it, you still get a 2 in the end. And I'm just hand-waving. As long as you somewhat believe that the total work I did in this array doubling is twice that I would normally do if I had an array of size n, that's enough. That's enough to understand what a dynamic array does. And if you're inserting 2n things, and overall you're only doing twice n work, that means that every insert, how much work are you doing? Like, what is the average amount of work you're doing every time you're inserting? Yes? Or order 1. So that means that even though there are some expensive steps, even though I will have a time when I insert and maybe my array is of size n over 4, and now I'm spending n over 2, which is a large amount of time. I'm just spending that to copy and insert. I mean, I'm just copying a lot of things. It would be steps in my execution, which would be really expensive. But if you analyze the entire thing together, and turns out you're only doing order 1 on average at each insert, which isn't that bad. So the moral is the dynamic arrays are not that bad. They're not that inefficient. They only do order 1 on average at each insert, even though they grow and shrink in size. And now the benefit is you don't have to know what n is. You can just have a dynamic array, and you can handle inserts and deletes without knowing the final size. Does everybody is convinced of that? All right, awesome. Let me see. Okay. All right, so when we talked about linked lists, we talked about pointers. So these arrows, these are the pointers in your linked list. And pointers are nothing but an address of some slot in memory. So this pointer is just a piece of information which says go to this location in memory, whatever that may be. And I don't know what language you guys are using, but in C, which is what Steve's been using, it's what is a star? Star P denotes the item pointed to by P. So P is a pointer, and if you want to figure out what element it's pointing to, it's star P, and ampersand X denotes the address of a pointer. So suppose I give you a pointer, it's an address in memory. Then in C, if you do ampersand X, then it tells you what element is actually stored at that location. So if you've taken some basic programming classes, or if you worked with pointers, you've probably already dealt with how to do pointer manipulation, and this is how you do it in C. And we'll go over this really fast because this is sort of, okay, so this is just defining a linked list. So you define what kind of item you're going to store in the linked list, and then let me use this. And this is the pointer. So here your items are names of presidents, Lincoln, Jefferson, Clinton, and then these are the pointers, which is struct list. As we talked about, this is Well, this denotes a pointer. So these are these pointers joining Lincoln and Jefferson and so on. And are these in order? I don't know enough about precedents, but of United States. Is this in order of the, okay, good. So this is a linked list of unsorted things. They're not in any particular order, which is usually how you use linked lists. How do you search, if I give you an element, how do you look for it in a linked list? And we talked about it briefly using pictures. There's no easy way to just go to an index. So even if you're searching for something, all you can hope to do is start at the beginning, follow the pointers, look at each slot, and hope that it's the one that you're looking for. And in the worst case, you just go through the entire list. How do you do that? Well, you can do this iteratively or recursively. What you do is you start at the head of the list. If this is just checking if the list is empty. So if the list is empty, obviously your thing you're looking for is not there. If it's not, you just look at wherever you are. You look at the item in that location. If this is something you're looking for, you're done. Else you keep going next in the list. So you go one step further in the list, and you keep looking. So what is the running time for searching in a linked list? We talked about this. Order n. Awesome. This is linear because in the worst case, you'll go through the entire list. And it's order because at each step, you're doing some comparisons. So that's just order one work. Suppose I had to insert into a list. How would I do it? How would I forget about the code for now? Just what is the idea if you're inserting into a list? Do you have to go to a particular location? Yes.
I guess it depends on where you're inserting, whether it's at the head, the tail, or in between.
Well, suppose I don't care. Suppose I'm saying add this to your pile of things.
Okay. So then really what you're doing is changing some pointers.
Yes. So what would be the easiest thing? Where would be the easiest location, at least in a single linked list, to insert an element?
At the head.
At the head. Perfect. So suppose I don't want to go through the entire list, and because I don't care where this element goes, I'll just go to the head of the list, and this is saying the address of the head of the list. So that's why there's 2 stars. So you go to the head of the list. Well, first you need some space for whatever element you're inserting. You don't care where that space is. So this is your list, and this is your RAM. That little chunk could be here. It doesn't matter. You allocate space for whatever you're inserting, and then you take whatever the head pointer was, and this becomes the head of the list, and it starts pointing to whatever the head used to be. So you allocate some space, and then now this element becomes the head of your list. So now this is the starting point, and you have a pointer that points to whatever used to be the head of the list, and that's how you insert in a linked list. And it might be worth sort of going through the code slowly, again later, but right now you just have to understand, what's the logic. When you're inserting, you don't care. You just make the element the head, and then you do some pointer manipulation. How much work is it? How much work is in running time, like in order notation? How much work do you do when you insert an element? Yes? Order 1, because all I did was that I changed a pointer and you allocated some space. That's order 1 work. Okay, this is long. Okay, how do I delete an element from a list if I only know? So there are 2 ways you could delete. I could give you the location where this element is and say delete this element which resides at this location. Or I could just tell you delete Jefferson from the list of precedents. I didn't tell you where Jefferson is. So if I gave you a pointer, you would just jump directly at that location, and you would delete that element from there, and then sort of. So this is your list. You just have the previous pointer point directly to the next element. And that's how you would delete an element. Suppose this is the logical sort of representation of your list. I say, all right, I send you directly to this cell by giving you the address. What you would do is you delete this, and you would do pointer manipulation where you would make this point to the next element. Or there could be a different case where I don't tell you where this element is, so you search for it, you figure out where it is, and then you do this pointer manipulation. You delete this element and make this element point to this element so that you have the list is maintained, the structure, pointer structure is maintained. So I think in this code, he's searching first, and then when he finds the element, he deletes it, and then he does the pointer manipulation. Any questions on how to delete in a list? We're not going through the code, but we can if you guys want to. I mean, we can stare at this for a while and make sure we're okay with whatever there is. Yes? Okay, so let me repeat the question. So the question is that suppose I had to delete from this list. Wouldn't it be easy if instead of sort of getting rid of this space in memory, I just copy the next thing here? And then what would happen? What would be the running time if I wrote a linked list that implemented delete like that? It's important to think about what else you would have to change. So the question is, suppose I deleted this element, I copied this element here. What would happen to this spot? You either delete it or you copy the next one here, and you do pointer manipulation and you keep doing it, and so on. What would be the efficiency or the running time for such a delete? Order n. Okay, great. Someone said order n. So what used to be an order 1 operation, yes? Yes, so this is what, so that's when you know where's the element you're deleting, right?
Then you don't need to look at the previous element. You can just do that. You already have a pointer where you want to.
Yes, and then which pointer would point to what?
So if you have 1, 2, 3,
Yes.
you want to delete 2.
Yeah.
Just copy 3 into 2 to the node, and
Mm-hmm.
then you just change words.
Oh, you change 1 pointer instead of 2. Okay, yeah, that works. That is true. You could make this even more efficient at an operation level. It doesn't change the running time, but it does make you do one less step at each time you delete. So you could do some tricks where you're, instead of doing 2 pointer changes, you're doing 1. And that's the sort of optimization that you could do. But right now, in terms of, as far as I'm concerned, I don't care if you're doing 2 pointer changes or 1, as long as it's constant many. So whenever you're talking about algorithms, you sort of blur out how, as long as things are constant and they're the order notation, order 1, don't care. Change 10 pointers for all I care. But when you're implementing it, you should care. I don't implement things, so I don't care. So are we sort of comfortable with deleting things from a list? Yes?
Oh, I think his point was if you didn't do it his way, you're going to get all of that.
I'm going to get OFN because I'm just changing this to here.
You can't go back. If you have the middle one,
Yeah.
it's a singly linked list. How do you have the guy to your left?
Oh, you're right. I can't go back. I was thinking of a doubly linked list. Never mind. Yes. All right. Don't do it my way. Do it whatever Steve's doing there, which I didn't read. Also do it the way he's saying, which is, I was thinking of a doubly linked list, which we're going to get to next, so this is a good teaching moment, even though I made a mistake, is that we can't go back in a linked list. So if you want to delete things, if I had a pointer to this element, I would take this pointer and make it point to here, but I don't have a pointer, so what I'm going to do instead is I'm going to copy this thing here, and I'm just going to go forward. So you can only go forward if you have a singly linked list. So you delete in a way where you only have to do forward pointer manipulation. What I was making you do was somewhat assuming that you could go back, but you can't. It's not a doubly linked list. We're going to talk about doubly linked list next, hopefully. Oh, no, it's the next one. All right, one more slide. What are the advantages of a linked list? I think we talked about most of this, so we can just go through this fast. Can a linked list be full? Can ever be a situation where you're like, I don't have space in this linked list, I need to double or anything of that sort? No, because it doesn't matter as long as you can find some space somewhere in your memory, you'll store your element there and you sort of store the address of that location, so you'll add a pointer. So linked lists actually never get full, so you never get overflow unless you actually absolutely run out of memory. So you don't have any memory left at all to store the new element. Insertions and deletions, as we saw, are simpler. Well, simpler in order notation. So in linked list, insertions and deletions are order 1. Why? But if you have an array and you sort of have to maintain some order, it's order n. So that's why simpler is in italics, because you have to do pointer manipulation, and you could be dumb like me and make mistakes and things like that. So they're simpler, as in they're efficient. And then the third point says when you have large records, moving pointers easier than moving things themselves. So suppose each of my item that I'm storing in an array or a list is really big. I don't want to copy it over and over if I'm using a dynamic array, because suppose that itself is, well, right now we're saying it's sort of constant. But constant, like operation, doesn't really capture more practical things. Suppose the thing you're moving is actually really big, so if you want to do practical optimization, you probably want to not move it and have pointers instead. So that's, again, what kind of use case do you have? What kind of elements are you storing in your array? Maybe if their size is huge, you probably don't want to move it over and over, and you want to use a linked list instead. So again, the trade-offs are different, and depending on what kind of application you have, you should figure out which one you want. So now, as we were talking about doubly linked lists. Doubly linked lists are nothing, they're nothing different or fancy. They're just a normal linked list with these back pointers. And it doesn't actually change the running time in an order sense. So yes, you will do more manipulations at any step, but if you do the order analysis, it's only constant factor different, whatever you're doing at each step. So doubly linked lists, you have the flexibility of going back and going forward, while a single linked list, you can only point forward. So this actually, if you're implementing this right, the size is not only constant factor different because you're only storing twice as many things. And the manipulation at each step is only double as it used to be. So if you think about the big O, the constant maybe changes inside the big O, but it doesn't really make the running time blow up. So if it's easier, in a sense, you could always assume that your list is doubly linked list. Any questions about doubly linked lists? Oh, and then I had to look this up, actually. I had to Google this. Singly linked list to doubly linked list is as a conga line is to a can-can line. I had to look that up. But you can look that up if you want. How many people know what that is? How many people don't know what that is? I guess the rest of you. All right, good. I feel better about myself. So if you want, you can actually look that up right now. It's a cute analogy. I can draw stick figures if you want. All right, I'm going to do it. I'm going to draw stick figures. You know that dance where people stand, like make a line, and this person is holding this person? It's a terrible figure. I shouldn't do it. So that's a conga line, and can-can line is when they're both holding each other and facing you and dancing like that. So first one is when you're sort of making a train of sorts, and the second one is when you're dancing with both your partners. So that's what this is. Okay. So we talked about this briefly. What is a stack? When we talked about what an operation is and how you implement it, we talked about a stack. And a queue is something similar. We've used it in English sort of language. A queue in computer science is when you have a list of things and you always insert an element at the top of the list, but when you, or whatever you call, you insert from one side, and then when you delete an element, you remove it from the other side. So suppose it's a line at a bank, and sort of this is the bank. I'm going to say bank, and these are people, and they arrive at different times. So in some sense, this guy arrived at t equal to 0. So he just went in, he's sort of at the head of the list, and then people joined, and they just made a queue behind him. Now when the counter gets free, who should be the one to go up? Who should be the one to be leaving or DQ from the list? Well, it should be this guy, because he's been waiting for a while until these people arrived. So he was the first in, and he should be the first out when there's a chance for him to actually go to the counter. So that's what a queue is. You look at the order at which things are inserted, and when you want to remove something from that queue, which you call a DQ operation, that means that whatever was inserted the earliest in time, that's the one that goes. And when you have a stack, we talked about this briefly, when you have a stack, you insert things, and this is the top of the stack, and when you pop, that's the thing that comes out. The top of the stack comes out. So the operations are the same. You're adding something and you're removing something. What happens if you're using a different sort of stack or a queue is what you actually remove and where the top thing goes. So in stack, you'll hear this last in, first out. So whatever was at the top is the one that left. And in queues, you have first in, first out. So whoever joined the line at the bank first is the first one to go to the counter. And why would you use these different things? Okay, so first of all, how would you implement, as we said, a data structure has operations. So we talked about operations. Now we're going to talk about implementation. How would you implement a stack versus a queue? So we talked about arrays and we talked about linked lists. So does it seem easy to implement stacks as linked lists? Now think about when you answer that question, think about what operations you have to do. You have to insert something at the top, and then you have to remove something from the top. Well, actually, you could do both. You could do linked list and array. But here, we're going to talk about arrays, because then you just have a counter of whatever the top of the list is. Every time you add something, your counter goes up. Every time you delete something, your counter goes down. I think that's what we're trying to say here. But I actually think you could do both, because inserting and deleting, at least from the top, is easier in a linked list as well. Now, if you had to make a tiebreaker, you would think about how you're going to use this stack. What are the other operations that you're going to do with it? What kind of things are you going to insert in it? So maybe you should do the tiebreaker based on that. And queues, you are more easily presented as linked list because you're doing the operations from either end. So you insert something and you delete something from here. I don't know. You'd have to take the word of Steve on this, but I would ask him twice, because I could argue on both sides, actually, that you could do queues as an array and stacks as linked lists. So I'm not gonna. So this is what he says, and I don't quite know. I'm not convinced by this argument, but that's something you should always sort of think about and ask questions about why something should be a linked list or why something should be an array. But right now, we're going to take him at his word. And it's true that all these operations in both these structures, you only take constant time. So you only do order 1 work. Is that clear? I'm not sticking up for this, and I would ask him myself. Maybe I'm missing something. So it's a good question to ask if he asks you what kind of questions you have from the lecture. All right, so we know what a stack and a queue is, and in fact, you would come up with a very explicit example very soon in the course when you start talking about graphs, where for one algorithm you'll use a stack and another algorithm you'll use a queue, and they're both traversal algorithms. They both will be how you traverse a graph. It's just that the way those algorithms work, stack would be very appropriate for one and the queue would be very appropriate for the other. So when you guys talk about depth first search in your class, you're going to use, I think for DFS you use a queue, or no, DFS you use a stack. Yes, that I know. DFS you use a stack, and BFS you use a queue. And once you actually find out what those algorithms do, you sort of know for yourself why you're using one versus the other. So they seem like they do the same thing, but one can be very useful than the other compared to the situation. Now this is the last 2 slides, and we only have, I guess, 10 minutes. That's a lot. So now the last thing that's going to sort of continue, this is going to seep through in the next lecture as well, is what is a dictionary or dynamic set operation data structure. So now these are data structures. There's a class of data structures that we call dictionary data structures. And it's very important to know what it means. So when you're studying algorithms, somebody might just come to you and say, well, that's a dictionary data structure, and you should know what they mean. They mean is that data structure supports these operations. So that data structure, you can search for an element. So first of all, let's look at what you have. Dictionary data structures are often in an ordered set. What you store is an ordered set, which by that I mean there's a key value pair that you're going to store. So there you have a set and there's a total ordering on it. So you have a bunch of elements. Suppose they're words, and so on. And suppose I say the total ordering is the alphabetical order of these words. So think about a dictionary. The dictionary is ordered by the alphabetical. You have all the words in an alphabetical order. And when you look up a word, you have something else that it points to, which is the meaning. So that's why these data structures are called dictionary data structures, because you get a key, and given the key, you search the data structure for what that key points to. So in dictionary, suppose I have to look up the meaning of conga, whatever that was. You go to that word, and then that's the key you have, and then you look up what it means. So that's the element you're storing at that location. So you have a key, and there's a total ordering on the keys. So here, actually I'm wrong, because these are the keys. This is not the set. They have a total ordering on them, which is the alphabetical order, and then when you pick a key, they point to some value. So there's a key value pair. So when you're searching, I give you a key, you look at your data structure, you tell me what this key points to. So key K returns some element or pointer to some element, which is what it's storing. When you insert something in a set, I give you an element, you go into the set, and you insert that element. So you just augment the set. Okay, so I don't tell you where to insert it, you just insert this element. When you delete an element, you go find that element and then delete it from the set. So again, given a pointer x to an element in the set, here it's saying it's the pointer, here it's saying it's the pointer. All right, both cases it's the pointer. Suppose I tell you to insert an element, you have a pointer to where that element is, you just go in and insert, and delete. I give you a pointer to where that element is, you go in and delete. But when you're searching, I'm giving you the key, and you're going based on the key and then telling me what element is there, or what is the pointer to the element stored at that location. I could ask you to give me the minimum of the set or the maximum. So remember, there's a total ordering on the elements of the set. So when I say give me the minimum, you give the first in this sort of logical total ordering that you have. When I tell you give me the maximum, you give me the last element in this ordering. Now, predecessor and successor is confusing because oftentimes people think that the predecessor and successor is the next element or the next sort of in the physical ordering that this set gets represented as. But predecessor is not what's the next element in space to you. It's the logical predecessor or successor. So it's you have an ordering of the set, and they have some logical ordering. Suppose it's the alphabetical ordering. So in that alphabetical ordering, what's the element? If you wrote out the elements in that ordering, what is the element that would be in front of me is the successor? When you implement it, it might be that whatever is physically next to you may not be what is logically next to you. You could try to store it in a way where successors and predecessors are not just in front of you and behind you. Because you could be storing it in not in the order where you're supposed to because of some reasons, because of the trade-offs in the operations that you get. So if you're using sort of a dictionary where everything is, the predecessor and successor are not the ones that are stored like right next to you, you have to think about what is the logical predecessor and successor. So for example, if you're thinking about alphabetical ordering and you're look at the list of people who teach you, Singh probably is the successor of Skiena. He made me say this, okay? So he said, give an example where because I'm not here, you're my successor, and your last name is Singh, and my last name is Skiena, and you're my logical successor, but not in a way that we're not sitting next to each other. So think about what the logical successor is. And I've made this mistake a bunch of times when implementing dictionaries. It sounds very high level for now because we haven't really implemented or looked at a dictionary, but it'll become clear when you actually implement it and you see how to come up with the predecessor or successor. So there's a different, again, as we talked about, there'll be a lot of ways in which you can implement a dictionary. And it's still like research areas where we still talk about, okay, a dictionary that does this fast and does this in this amount of time. So we're still doing research and implementing dictionaries that sort of optimizes on one operation, but it might give you a trade-off in the other operations. The key is you have a bunch of operations. You can't make all of them that fast at the same time. You can't have a dictionary which does everything in order one. If you optimize something, you might lose out on something else. So if you optimize on search, you might lose out on insert or delete because you'll implement it in a way to optimize search. So that's sort of one of the last things. All right, we're going to have to come back to this because this is what anyway, never mind. I think we're done. You can read the last two slides, and that's what the next day's problem is based on. It's based on the last two slides. All right, thank you, guys.
I have a question.
Yeah.